In the last class, we have seen how to compute the volume of a solid which is obtained by rotating a plane region around an axis, so a solid of revolution. Now, there are many solids which are not of revolution, okay, and so the question is, how do we compute the volume of a solid that is not of revolution, okay? What kind of solids am I talking about? Well, many solids that actually have some practical applications and for which we do want to compute the volume. For instance, like the brain or a boat, or, well, is that a boat or a guitar? I'm not quite sure. Or some kind of futuristic car or anything like that. So again, each one of these objects has a volume which for some reasons may be important to compute. But how we're going to compute it? None of these is a volume of revolution. Well, the problem of computing this volume in general is quite difficult, and in fact, there is a more general solution involving more complicated types of integrals that you're going to be looking at next time. I mean next year in your second year. However, there is one situation where if we know one key piece of information, then we can use the slice, approximate, add up, take the limit process. Okay, so what we're going to look at is what is this one situation, why is it so critical, and once we have that situation resolved, or under the assumption that that particular situation does occur, then we're ready to go. Let's see how this is done. So this is what we call the slicing method, okay? And so what we're going to do is we're going to start from an object like this, and the first thing that we need to do for this method is we're going to line up the object whose volume we want in a particular way, okay? So what we're going to do is we're looking for the volume of this thing, we're going to lay it along the x-axis in a special way. What criterion describes the special way? You'll have to wait for a second because I have to show you what the next step is in order for you to understand how to what the criterion for lying it along the x-axis is. Okay, but for now, let me say that in this particular situation, this would be a good way of lining up the object along the x-axis. This is the way that traditionally the brain is laid out when you take pictures with a CAT scan, right? And that's exactly actually what we're going to do. Not a CAT scan, but something similar to it. So what we're going to do is going to use our usual procedure. So we're going to slice up this object, this brain, again, just like a CAT scan will do. And then we're going to approximate the volume of each slice. How we're going to approximate that volume? First of all, by approximating the area of each section. So what we're going to do is we're going to take each one of these sections, see what it looks like, and then, and this is the critical step, we must have laid out our object along the x-axis so that we have a way of computing the area of each of the slices that we get in this way. So that's the criterion that we need to use to lie, not to lie. We don't want to lie. Lying is not something we're supposed to do, are we? So we want to lay the object along the x-axis, and we want to do it in such a way that, again, once we do it and once we take these slices that we're looking for, their area is known. So let's say for each x, we know exactly what the formula a of x is. And at this point, once this is done, the rest is easy, because then the rest, remember, consists simply of, first of all, multiplying by delta x, so that we end up with the volume of the slice. Remember, a of x is just the area. We multiply by the thickness, which is still going to be delta x, and it gives us the volume. Then what we're going to do is we're going to add up all of the volumes that we've obtained in this approximate method. And then, of course, we're going to take the limit, and that creates the very familiar integral from a to b, whatever the beginning and the end points of the solid are, of the function of a of x dx. Probably this formula looks a lot easier than the formula for the disks, washer, or shells method. But remember, a of x itself may be a fairly complicated function. So in fact, just try and imagine what the area that describes the, what the formula that describes the area of a section of the brain is for each of the values where the brain occurs on the x-axis. Probably that a of x is not going to be that easy. So as long as we are dealing with a function that we can identify, we can construct, we can describe in terms of x, and then afterwards we can integrate, then this problem is done. If that a of x cannot be obtained, or if the a of x can be obtained but it's a really messy thing that we cannot compute, then we're stuck again. But again, it is a method, it can be used, and we're going to see how to use it in class.